Okay, Chapter 4, Probability. So we have our basic rules of probability that they go between 0 and 1. They can't be any less than 0 and they can't be any more than 1. And the probability of A equaling 0 means that the event will not occur. If it equals 1, it means the event will surely occur. And if it equals a half, for instance, anything in between is what percent of the time it's going to happen in the long run. All right, so a probability of A equals a half as event A will happen 50% of the time in the long run. All right, so the first foundational rule is that they go between 0 and 1. And the second one is that if we, what we call disjointify our sample space so that we have all these separate non-overlapping events, that the probability of all of them add up to 1. So it's kind of like if you have all the pieces of the pizza, you have 100% of the pizza. All right, so the complement rule is the first rule that we'll learn. This one is kind of obvious, but when you are working on complicated probability questions, it might not seem obvious. All right, so the probability of the complement of an event, and that's what this notation is, A, that looks like it's written to the C power, that's read as A complement. So the probability of A complement is equal to 1 minus the probability of the event. All right, so probability of A complement is 1 minus the probability of A. So this should make sense. If we have a 30% chance of rain, what's the probability it's not going to rain? There's a 70% chance it's not going to rain, right? So technically probabilities go on the scale from 0 to 1, but lots of times I change that to a percentage and talk about it in terms of chances because our human brains seem to function better thinking about percents. All right, so for example, globally 12% of men and 10% of women are left-handed. What's the probability that a randomly selected woman is not left-handed? Well, clearly if 10% of women are left-handed, 90% are not left-handed, okay? But let's just work on our rule because remember I said later it might seem like it's hiding in plain sight and it might not be so obvious. All right, so the probability of not being left-handed is 1 minus the probability of being left-handed, which is 1 minus 0.1, which is 0.9. All right, the union rule is sometimes known as the addition rule. That is the probability that event A or B occurs, so or at least one of the events is the probability of A union B, so this symbol is the union symbol and it goes with the word or, is the probability of A plus the probability of B minus the probability of A intersect B. So this symbol is intersect. And this symbol is union. So the intersection symbol is kind of like the upside down union symbol. All right, so let's draw a picture of this so that we understand what's going on. So we're going to start to think about probabilities as the size of them relative to the size of the sample space. So if I've got my sample space S here, and I've got my event A, and I've got my event B, and I wanted to think about the probability of the union of these two. That is the whole stuff inside the blob of A union B. Okay, so everything inside that darkened area. How could I get that? Well, I could take the size of A, which is the probability of A. So it's like taking the size of the circle add it to the probability of B, the size of circle B. But what happens, now that you see the picture, what happens when I add the size of circle A to the size of circle B? I counted where they overlap, that part got counted twice. So what I do is I just subtract out that intersection once. And that's where that formula comes from. All right, so for example, in the US, 23% of adults get no physical activity, 76% eat fewer than 5 servings of fruits and vegetables, and 19% qualify for both of the previous chronic health risks. What is the probability that a U.S. adult has at least one of these risks? Well, we can use our union rule. We can compute the probability of one or more risks as the probability of no physical activity, so that's like the size of the physical activity circle, plus the probability of poor eating habits, so that's like the size of the poor eating circle. And then remember, anywhere they overlap, we counted that twice if we added the size of both of those events. And so we're going to subtract out the intersection once, okay? Notice that the word and is interchangeable with intersection, okay? And the word or is interchangeable with the union word. All right, so we've got these probabilities from the blurb. 0.23 plus 0.76 minus 0.19 equals 0.8. All right, so two events, this is a definition, A and B are said to be disjoint or mutually exclusive if they share no outcomes in common. That means they don't have an intersection. So in my Venn diagram, the way that I would draw that is circle A and circle B would not overlap. So the probability of their intersection, of A and B intersecting, is 0. So that's what it means to be disjoint. That's kind of like a property that you can picture. It's like a physical property that is pretty easy to picture. All right, so for example, Samantha rolls a regular die. What's the probability she rolls either a 1 or a 6? Well, that's the size of the circle for a 1 plus the size of the circle for a 6. So the size of the event for a 1, the size of the event for a 6. Remember, we're double counting the intersection, so we have to subtract it out once. The probability of rolling a 1 and a 6. But here, they're disjoint. You can't roll a 1 and a 6 at the same time, so the size of the intersection is 0. So you end up getting 2 6. So what's the probability she does not roll a 1 or a 6? Well, that's our complement rule. So that's 1 minus the probability of a 1 or 6, which is 1 minus 1/3, which is 2/3. All right, or you can directly compute it. You can think about what is defined as not a 1 or a 6. That's a 2 or a 3 or a 4 or a 5. Those are disjoint. So you can only roll 1 at a time. So it's the probability of a 2 plus the probability of a 3 plus the probability of a 4 plus the probability of a 5, which is 4 1/6, which is 4/6, otherwise known as 2/3. Okay, so we've just kind of applied this being disjoint phenomenon to our union rule to see how that works. So when you have disjoint events, you don't need to subtract out an intersection. All right, so another definition. If two events are independent, that means the occurrence of one event does not affect the probability of the occurrence of the other event. This is more of like a theoretical probability, a little bit more difficult to picture. So for example, 2 flips of a coin are considered independent, 2 rolls of a die are considered independent, and 2 spins of a roulette wheel are considered independent. Independence is when knowledge that one happened doesn't give you any more information about the other one happening. So if the probability of both A and B happening, that's the intersection, equals the product of the individual probabilities of A and B, then A and B are independent. That's how we mathematically know whether two events are independent. So the probability of the intersection, if it equals the probability of A times the probability of B, those events are independent. And it turns out that this works the other way. So if A and B are independent, then we automatically know the probability of both A and B happening is the product of their probabilities. So it works vice versa. All right, so Maurice rolls a regular die. What's the probability he rolls a 1 and then a 2? Notice the word and, that means we're computing an intersection. So a 1 and a 2, since the dice rolls are considered independent, is the probability of a 1 times the probability of a 2, which is 1/6 times 1/6, otherwise known as 1/36. All right, let's try another one. What's the probability he rolls either a 1 and then a 2 or a 3 and then a 4? So notice that we're going to compute an intersection and another intersection, and then we're going to add those two intersections together using our union rule. So the probability of 1 and a 2 or a 3 and a 4, since these are independent, we can take the probability of a 1 times the probability of a 2 for the probability of a 1 and then a 2. Take probability of a 3 times the probability of a 4 to get the probability of a 3 and then a 4. And then these are disjoint, so we can just simply add, and we don't have to subtract anything back out to complete our union. All right, so it's 136 plus 136, which is 236. And what is the probability that he rolls a 6 and then flips a coin that shows tails? Notice the word and, so that's going to be one of our multiplication rules. Obviously, these don't depend on each other. They're independent, so we can simply multiply the probability of a 6 times the probability of a tails. Probability of rolling a 6 on a fair 6-sided die is 1/6. Probability of flipping a tails on a fair 2-sided coin is 1/2. 1/6 times 1/2 is 1/12. All right, so there's some basic applications of our probability rules. Let's try one that's a little bit trickier. So I just want to show you here how we can use our rules, even for one that's a bit trickier, to get the answer. Okay, so a broadcast meteorologist gives the following forecast: a 20% chance of rain on each of the weekdays in a week. And a viewer is having an outdoor event Monday through Friday and wants to know the probability that it will rain. Assume precipitation is independent for each day, so we can do this example. That is probably not true, but we're just going to assume it for the sake of this example. And we're going to compute the chance that it will rain at least one day. Now, this is a little bit trickier of a union problem than we've had previously, but I'm going to show you how we can use some basic reasoning and our probability rules to get the answer. All right, so how do we compute this? Well, the probability it's going to rain at least once is the probability it will rain on Monday or Tuesday or Wednesday or Thursday or Friday. Remember, the union symbol goes with the word or. So we have a union rule that's a little more complicated because we don't just have two events that intersect. We've got a five-way intersection, we've got four-way intersections, three-way intersections. There's lots and lots of intersections to keep track of and keep adding and subtracting back in. So let's use a little trick and use the complement rule. So we can rationalize that the probability it will rain on Monday or Tuesday or Wednesday or Thursday or Friday is 1 minus the probability that it doesn't rain at all, that it's sunny every day. So just a simple little trick with our complement rule. So that is 1 minus 0.8, so that's the chance it's not going to rain on Monday, times, since this is sunny every day, so it's not going to rain on Monday and not going to rain on Tuesday and not going to rain on Wednesday. So instead of a union, we've got intersections now, and they're independent. We're going to assume that for this example, so we can just take 0.8 5 times each other. And that ends up giving us a 0.67 or 67% chance. All right, so now let's talk about the general intersection rule. So the intersection rule for two events both occurring, this always works whether they're independent or not, is the probability of A intersect B is the probability of A given that B happens. So that vertical slash means given, times the probability of B, or the probability of B given A times the probability of A. So that's your general intersection rule for computing your ands, your intersections. Little sidebar real quick. Notice that when events A and B are independent, the probability of A given B equals the probability of A. If knowledge that B happens doesn't change the chances for A happening, you can just drop the condition. And accordingly, the probability of B given A, if they're independent, A doesn't matter. Doesn't matter if you're given that A happened. If they're independent, then it's just the probability of B. And when two events A and B are mutually exclusive, the probability of A given B equals 0. Okay? If they're mutually exclusive, they're disjoint and they don't overlap. And so the probability of A given that B happened is 0. Because why? Because if B happened, you know you're inside this circle, so A couldn't have happened. And similarly, the probability of B given that A happened is also 0. All right, so what I'm doing here is just a simple little algebra rewrite. So I'm taking my intersection rule and I'm dividing both sides by the probability of B. And I get this formula. The probability of A given B is the probability of A intersect B divided by the probability of B. So we now have a formula for calculating conditional probabilities. Now, what I want you to think of when you see that you need to compute a conditional probability, that is the probability of A given that some other event B happened, I want you to just think in your mind like a little mantra. That's the probability of their intersection divided by the probability of the thing you're conditioning on. So the probability of the intersection of these two events divided by the probability of the thing you're conditioning on, which is called B here. So let's do some examples. So we've got the probability of finding a job within 3 months is 0.8, and the probability of having prior work experience is 0.4, and we're telling you that the probability of finding a job within 3 months and having prior work experience is 0.35. Now, given that a student has prior work experience, internships, etc., what's the probability they will find a job within 3 months of graduation? So I want you to write down your probability statement first when you have a probability problem to attack. It sounds kind of oversimplified, but that's going to get you started out the gate and get you off and running in the right direction. I always recommend writing down the probability statement. Don't skip any steps here. It's very easy to make a mistake. All right, so given that they have prior work experience, we want to find the probability of finding a job. So that's how we know that we need to write our conditional statement as the probability of finding a job given that they have prior work experience. So that's how you know what comes after the condition. Whatever's given comes after that condition. And now that we see that conditional probability statement, we know how to solve this, right? That's your little mantra. It's the probability of their intersection divided by the probability of the thing you're conditioning on. So it's the probability of job intersect experience divided by the probability of experience. And we have both of these given in the example blurb above. We have the probability of a job and having experience, that's 0.35, so that's our numerator. And we have the probability of prior experience as 0.4. And so we just fill those in, punch it into a calculator, and get 0.875. All right, let's try another one. An economist predicts a 60% chance that country A will lower interest rates and a 25% chance that country B will lower rates. There's also a 16% chance that both countries will lower rates. What's the probability that country A drops its rates given that B does? All right, so let's write our conditional probability statement. That's the probability of A dropping its rates given that B does. So it's the probability of A given B. And we have our little mantra. That's the probability of their intersection, A intersect B, divided by the probability of the thing you're conditioning on, B. So probability of A intersect B divided by the probability of B. And again, we have these in the question. The probability of A intersect B is 0.16, and the probability of country B dropping their interest rates is 0.25. So 0.16 divided by 0.25 is 0.64. Hopefully by this point you're feeling a little bit better about these conditional probability formulas. All right, so now I have another question. Can we determine if country A and country B are acting independently of each other? Well, what's our definition of independence? That is, we can check whether the probability of the intersection of the two events equals the probability of each event times each other. So let's check it. Well, we have the probability of A intersect B from the blurb. It's 0.16 because there was a 16% chance that both will lower their rates. So now we can just multiply the probability of A times the probability of B lowering their rates to see if that equals 0.16. Well, it turns out that it doesn't. The probability of A lowering their interest rates is 0.6 and the probability of B is 0.25, and those multiply out to be 0.15. So the probability of their intersection doesn't equal the probability of the two events times each other. And so A and B are not independent, they are dependent. So make sure that you write that they are dependent in your notes. They are not independent. Okay, another example. The probability that a librarian owns a fish is 25% and a dog 40%. However, the probability of owning a fish if a librarian already owns a dog is 10%. We want you to find the probability that a librarian owns both a fish and a dog. So again, write down your probability statement. Here, we want to know the probability of fish and dog. So that's intersection. Probability of fish intersect dog. And we've got probability rules for that, right? So that's the probability of a fish given a dog times the probability of a dog. If you didn't remember that right away, not a problem. You can put these probability rules on some little flashcards and you'll have them memorized in no time flat. All right, so the probability of a fish given a dog times the probability of a dog. And we have those from the blurb. The probability of owning a fish if the librarian already owns a dog is 10%, so that's 0.10. And the probability of a dog, the chance is 40%, so the probability is 0.4. Those multiply to be 0.04. Okay, so now we're going to learn a law of total probabilities and Bayes' theorem. And this may be something that you didn't get to in your previous stats classes. All right, so we're going to show you, though, that with these probability rules, you could have already computed this. Now, it would have been a little bit of a stretch. I would have had to probably pull you through several ways of thinking, but your basic probability rules do extend to allow you to solve this problem. So let's suppose we have these two buckets of marbles, and they're behind a curtain, and without looking, you reach back and pull one marble out of a bucket. Given that you pull a blue marble out, what's the probability that it was from bucket 1? All right, so first let's write down our probability statement, what we want. We want to know the probability that you're from bucket 1 given that you pulled out a blue marble, right? That's from the blurb. Probability that it was from bucket 1 given it was a blue marble. Okay, and we know a probability rule for that. That's the probability of the intersection of being from bucket 1 and being blue divided by the probability of being blue. All right, but what do we have? Do we have everything we need to solve that? Let's figure out what we have. So we have the probability of being a blue ball given that you're from bucket 1 is 0.5 because there are 5 blues and 5 reds in bucket 1. We have the probability of being blue if you're from bucket 2, right? What is it? There's 1 blue and 2 red balls in bucket 2, so that's a 1/3 chance. We also have the probability of being from bucket 1. We're going to just call that a half. We're going to assume that you have a 50-50 chance of reaching in bucket 1 or bucket 2, and therefore the probability of being from bucket 2 is 0.5. So we know what we want, we know what we have, and now let's figure out how to put these together to get our answer. So we're going to use a tree diagram. All right, so for our tree diagram, we're going to start out our branches as our condition. We have that the chance of being from bucket 1 and bucket 2 is 0.5. So we're going to label our first 2 branches bucket 1 and bucket 2 with a 50-50 probability of being from either of those buckets. Now, if you're from bucket 1, you've got 2 choices. You can be a red marble or a blue marble, right? So we're going to draw a blue branch and a red branch from bucket 1. And what's the chance that you're a blue marble given that you walked up the bucket 1 branch? 0.5. There are 5 blues and 5 reds in that bucket. And of course, that means that the probability of being a red ball, if you're from bucket 1, is also 0.5. All right, now let's suppose you walk down the bucket 2 branch. You got 2 choices. You can be a blue or a red marble again. But here, the chance of being a blue marble, given that you walk down the bucket 2 branch, is 1/3. And so the probability of being red is the other 2/3. So we've got our tree diagram labeled. Now, do you remember what the tree diagrams mean? How you use them? Well, if you walk up a path and multiply the probabilities, if you remember, you get intersections, okay? So the probability of being a blue marble and being from bucket 1 is multiply the probabilities up that path. So multiply these probabilities till you get to that. 0.5 times 0.5 is 0.25. The probability of being from bucket 1 and being a red marble is 0.5 times 0.5, 0.25. The probability of being from bucket 2 and being a blue marble is 0.5 times 0.33, which is 0.165. And last but not least, the probability of being from bucket 2 and being a red marble, multiply those probabilities, is 0.5 times 0.67. Perfect. All right, so we've got these intersections. So it's looking like we're starting to get at our answer. Remember, we wanted to compute the probability of being from bucket 1 given that you're a blue marble. And we needed the probability of being from bucket 1 and being blue. We have that numerator now, right? We've got it sitting right here. We now know that that's 0.25. And we also have the probability of being a blue marble for that denominator. How many of these paths result in being a blue marble? This one does, and this one does, right? This path right here results in being a blue marble, and this path results in being a blue marble. So we've got our numerator. The probability of being blue and from bucket 1 is 0.25, And now we need to figure out that denominator. Well, there are two ways that you can be blue. You can be blue and be from bucket 1, or you can be blue and from bucket 2. So all we do is apply that word or, those are disjoint, and just add those two intersections. So we've got 0.25 divided by 0.25 plus 0.165, and it turns out to be 0.6. So pretty cool. We took what was sounding like a complicated problem and we broke it down into its parts using our probability rules that we already learned, and we ended up getting the answer. Now let's examine exactly what we did here. We computed the probability of being from bucket 1, given that you're a blue marble, by applying our little rule. That's the probability of their intersection divided by the probability of the thing you're conditioning on, the probability of being blue, which is also the probability of their intersection divided by, instead of just writing it as the probability of being blue, I can write it as the probability of being blue and from bucket 1, or the probability of being blue and from bucket 2, right? So that's legitimate. That's the only two ways you can be blue, so we've just broken that down into a further breakdown. And we can go one step further, and we can remember our probability rules that create intersections. So in our denominator, instead of writing the probability of being blue and from bucket 1, we're writing it as the conditional probability times the probability of the thing you're conditioning on. The probability of being blue given bucket 1 times the probability of being from bucket 1. And similarly with the intersection of blue and bucket 2. So we've just rewritten our original probability statement in a different way using our probability rules. This turns out that you've actually used a kind of complicated looking theorem called Bayes' theorem. All right? Bayes' rule says if you have A1 through AN disjoint and exhaustive events, and B is any event, then for J equals 1 through N, the probability of AJ given that B occurred is the probability of their intersection divided by the probability of the thing you're conditioning on. And we can rewrite it just like we did that last question. It's the intersection written as the conditional probability times the thing you're conditioning on, and the denominator, the probability of B, written as all the intersections plus each other, just like we just did. So that's actually Bayes' theorem. And that bottom piece is the law of total probabilities, that you can kind of turn that probability statement into these intersections added to each other. All right, so let's picture what this Bayes' theorem is. So it says that the probability of any one piece of this A, given that B happened, and I just happened to just select A1, so we didn't have to put a J there. We're going to picture something concrete. How could we compute the probability of A1 given that B occurred? Well, that is, once you've got given that B occurred, you can erase everything other than B, okay? Now, there's still a piece of A1 and B, a piece of A2, A3, A4, and A5, but anything outside of B did not happen once I tell you that B happens. So, I can write this in terms of Bayes' theorem, right? It's the probability of their intersection, A1 intersect B, which is written here in the numerator. That's the probability of A1 intersect B. And that's pictured right there on your picture. And then the denominator is just the probability of B. So it's your conditional probability rule. It's the size of A1 relative to the size of the sample space, which is now B, because we conditioned on that happening. So there's a picture of Bayes' theorem for you. All right, so now let's apply this to a different example. Suppose we have machines 1, 2, and 3 producing the same product, and the rates of defectives from each are 2%, 1%, and 3% respectively, meaning 2% for machine 1, 1% for machine 2, and 3% for machine 3. And then suppose the percent of the total product made by each machine are 35, 25, and 40% respectively. So 35% come from machine 1, 25 from machine 2, and 40% from machine 3. And we want to find the probability that a randomly chosen defective was produced by machine 3. So first, let's write down our probability statement. We want the probability of being from machine 3 given that you're defective. So now let's consider what we have. Well, we have the probability of being defective given from machine 1. That was 2%, 0.02. Probability of being defective given that you're from machine 2 is 0.01. And the probability of being defective given that you're from machine 3 is 0.03. Remember, that was given in the blurb on the previous slide. And what else do we have? We have the probability of being from machine 1, right? That was 0.35, 35%. We have the probability of being from machine 2. That was 25% or 0.25. And the probability of being from machine 3 is 0.4 because there was a 40% chance of being from machine 3. So that's what we were given in the blurb. And now we can put this all together using Bayes' theorem to find the probability of being from machine 3 given that you're defective. So how do we do this? We apply Bayes' theorem. We do the intersection of being from machine 3 and defective in the numerator. So that's the probability of D given 3 times the probability of being from machine 3. And then we can disjointify that sample space, okay? And we can add the probability of being defective and from machine 1 to the probability of being defective and from machine 2 to the probability of being defective and from machine 3. And then we just simply need to pop in our numbers that we had on the previous slide. So the probability of being from machine 3 given D, after we plug in all the numbers and crunch it in our calculator, ends up being 0.558. So there is a fully worked example of Bayes' theorem, and you have done it.